Thanks for joining me in today's lesson. In this tutorial, we will use formulas to solve real-world application problems. So we're in section 4.7 and 4.8, and here is your formula sheet. I'd like to make a few notes about the formula sheet. First of all, I'm not going to make you memorize these formulas, but you will need to know what the pieces mean and where all of the numbers go. You will not be able to use this formula sheet on the test or quiz. I will give you the formulas though. So get to know these formulas. I know that you can read this sheet, but I want to point out a couple things. When it talks about the initial amount, n being the initial amount, whether it's the number of organisms or cells, or in terms of p, the principal, the initial value of your money, or right here, the initial, all of these initial amounts go right here is as the coefficient in your formula. The initial amount, what you're starting with, will always be the coefficient in the formula. And what that amount becomes, whether it's decaying into something or growing, hopefully with your money is growing, that's on the other side of the equal sign. So the initial goes as the coefficient, and what it grows to become or decays to become is on the other side of the equal sign. T is time, and it should tell you what that's measured in. R is a rate. Watch out for your rate. If you have something like 7.5%, that is the number 0.075%, means to divide by 100 or move the decimal point 2 places to the left. So make sure that when you're plugging in a percent, you're using the actual number that it is. So that's what R is. You have N's. You go ahead and read this formula sheet and get to know this as we work through these problems. So let's look at example 1 and example 2. These problems are almost identical. There's only one change. In this first one, we're compounding our money twice per year, and in the second one, we're compounding continuously. Everything else stays the same. We're investing $500. It's at a 6% annual income or annual interest rate, and we're trying to see how long it's going to take to double to 1,000. So I'm interested to see how long it takes if we're compounding twice a year versus if we're compounding continuously. So let's figure out what formulas we're using. For this first one, since it's a certain number of times per year, we're plugging into that third formula, A equals P times 1 plus R over N to the NT power. That's the formula that we're using. So how much money are we starting with? We're starting with 500. Like I said, what you're starting with will always go here as the coefficient. What it's turning into will be on the other side, and that's what the 1,000 is going to be. We want to see when it grows to 1,000. 1 is a 1, plus is a plus. The R is the rate, and 6% is 0.06. N is the number of times compounding, and that is twice, so that is 2. And it repeats itself again up here. And then the only unknown I have is t, which makes sense since we're solving exponential equations, that would be up in the exponent. So if I'm solving for t, I need to get rid of all of these other numbers. And they're each going to go one at a time. So the one that's farthest away is usually the one that goes first. So I'm going to divide this 500 out of here. Divide to both sides. That's just a coefficient, so it's usually the first thing to go. 1,000 divided by 500, of course, is 2. And over here, I'm going to get this base to be together. 0.06 divided by 2 is just 0.03. And 0.03 plus 1 is just 1.03. So that's not too bad. I don't need it in parentheses. I'll keep it in parentheses. Raised to the 2t power. So there's my equation. The base is isolated like it needs to be, and now I can take the common log of both sides, or the natural log of both sides, or in this case I might take the log base 1.03 of both sides. Also, maybe I just convert this out of exponential and into logarithmic form. So now we're looking at this equation right here, and in a previous tutorial we looked at 3 different ways to solve this exponential equation. And I encourage you to do whichever way you would like to. What I'm going to do, and I'm kind of running out of room, so I'm going to do it over here. I like to do the double arrow whenever I'm converting. I'm just going to convert out of exponential and into logarithmic. And I'm going to rewrite this as the log base 1.03 of 2 is equal to 2t. I'm just converting it out of exponential and into logarithmic form. T is almost solved for. All I would have to do is divide by 2, and I'll have what T is. And I'll put my little approximate sign. I need to do the log base 1.03 of 2 and then divide that by 2. And I'll just do that on the calculator. If you don't have the calculator that you can do this log base when you press math and then up, if you do not have this log base, then you will need to do the change of base formula, which is the common log of 2 divided by the common log of 1.03, and then divide that by 2. Watch out for your parentheses, of course. If you do have this function on your calculator, you can go ahead and do it basically in one step. There's my base, and there's my number, and I'm going to divide that by 2. I get 11.725 if I correctly round. 11.725. So 11.725. These are all word problems today, and word problems end in words, and we know that we're measuring in terms of years. So just under 12 years, we will have doubled our money. Not a bad deal. 6% is a pretty good interest rate right now. So example 2 is almost identical, except remember the buzzword continuously. That's the PERT formula. A equals P e to the RT. The numbers are basically going to go in the same spots, the 500 and the 1000. So I have 1000 here. The 500 is my coefficient. E is E. My rate is still 6%, so 0.06. And T is what we don't know. We have to isolate the base before we do anything else. That's why the 500 is going to divide first, and I'm going to have 2 is equal to e to the 0.06t. Since I'm dealing with base e, I'm going to be using natural logs. So I can either convert like I did before, or take the natural log of both sides. That's what I'm going to do. I'm going to say the natural log of 2 is equal to 0.06t. Remember that the natural log has that little base, so I can convert that, and now all I have to do is divide by 0.06, and I'll have what t is. T is approximately, let's plug this into the calculator, and I have the natural log of 2, close that parenthesis, and I'm dividing by 0.06, and I've got it, 11.552. 11.552 years. So a little bit faster. Yeah, maybe a couple months. When we're compounding continuously, our money will double just a little bit faster than if we were compounding twice per year. Now, if you don't like this conversion right here, some people might just take the natural log of both sides, take the natural log of 2 and the natural log of e to the 0.06t. But again, remember that the natural log of e goes away, and you'll have the natural log of 2 equals 0.06t, which is exactly what I had converted to anyway. So let's look at our next example, example 3. A certain type of organism can grow from 30 to 195 organisms in 5 hours. Oh boy. Find K for the growth formula. Okay, so we're using our first formula. That's the y equals ne to the kt. And we just have to plug some numbers into here. So what we're starting with in this case is the 30, and that's always going to go right here as that coefficient. What it grows to become, and it does grow in this case, to 195 organisms. Hopefully these are good organisms to have around. E is, of course, E. K is what we're looking for. T is time. And in this case, it's good to note that we're talking about hours. And that, of course, is 5 hours. So we'll put the 5 right there. So we need to solve this equation, and I'm going to start to get everything away from this K. The first thing to go is this coefficient. So let's divide by 30. And 195 divided by 30 becomes 6.5. And this is e to the, if you don't mind, I'm going to write this as 5k instead of k5, so I don't need the parentheses. And there we go. We could take the natural log of both sides. Natural log of 6.5 is equal to the natural log of e to the 5k. That natural log of e will then go away, and I'll have that, I'll just write it as 5k is equal to the natural log of 6.5. Just divide by 5 and I believe we'll have our answer. K is just a constant. And in this case, let's see what we have in our calculator. Let's see, we've got natural log of 6.5, close that parenthesis, and then divide by 5. And our constant right now is 0.374. So 0, I always like to start with the 0, 0.374. So this is a constant, and in this case, that represents organisms per hour. That's what this constant represents. Of course, we're growing. That's why the constant is positive. If the constant were negative, then we would be decaying, and it would be decreasing. So this is increasing about a third per hour. So let's look at example 4. Example 4, we have an investment service, and they promise to triple our money in 12 years. Well, that's fantastic. In the previous two, the first two examples, we were doubling in just under 12 years. So tripling in 12 years, I would definitely take this. It says assuming continuous compounding of interest, there's that buzzword, continuous, what rate of interest is needed? So since I know that we're continuous, I know that it's the PERT, A equals PE to the RT, and I'm going to be plugging numbers in here. Although in this case, I don't know how much we're starting with. It doesn't say how much money we're investing. It just says that we're going to be tripling. So I guess you could pick whatever you want. If you want to put in $500 and let it triple to $1,500, or if you want to put in $1 million and triple to $3 million, that would be great. But you know what I'm going to do? I'm going to put in $1 whole, and I'm going to let it, over 12 years, grow to become $3. That's right, 1 turns into 3. You might laugh at me. I understand waiting 12 years for $1 to grow into $3, but think about the very first thing we're going to do to solve this equation. So far, the very first step that we've done is divide by the coefficient. So if you choose $500, great. You're going to have to divide by 500. If you choose 1 million, great. You're going to be writing a couple zeros and then dividing by 1 million. I'm going to put in 1 so that I don't have to divide by anything. So R is, I believe that's what we're looking for, and we do know that it's going to take 12 years for this to happen. So again, you can put in whatever number you want for P and understand that this is going to be 3 times P. So whenever you divide by whatever P is, you're going to have a 3 over here. I put the $1 to the $3 because I think that that's funny, and mathematically it's a little bit more efficient. So I need to get to this R. I'm going to take the natural logs again, since I'm dealing with base E. I'll take the natural log of this E to the, I'm going to write it as 12R. The natural log of E basically goes away, and I have the natural log of 3 is equal to 12R. Divide by 12, and I'll have my answer. I'll come up here. R is going to be approximately, I need the natural log of 3 divided by 12. So that is going to be, natural log of 3 divided by 12, there it is, 0.092. 0.092. 0.092. That's what R is. But of course, if we're going to write the answer to this, they're looking for the rate of interest. So this is actually what the number R is. But if I want to convert that to a rate, I'm multiplying by 100. This would be 9.2%. To answer this word problem, that is what we're looking for, something with our units. It's a percent. That's a really good interest rate. If you can find something like that, put your money there. 2 more examples. Let's look at example 5. This is an example I pulled from the book. The United Nations created the following population model based on data from 1990 to 2002. Okay, so it might be some old data, but let's see what we've got. It says that the population is 5.451 times e to the, this big constant, and then t. T was between 0 and 12 because they took 12 years of data. The population is in billions, so P is measured in billions, and it says that T equals 0 represents the year 1990. Okay, that makes sense. So it says, when will the world population reach 7 billion people? Well, I believe we've already made it to 7 billion people. But let's see what happens. I'm going to take this 7 billion people and I'm going to plug the 7 right in there. Now remember, P is measured in billions, so I don't need 7 billion to plug in there. I really just need the 7 to plug in there. So 7 is going to equal the 5.451 e to the, let's see if I can get this constant correct, 0.1165 t. And there we go. So it's not a difficult problem. I just had to plug a number in to the model that the United Nations had created. And now I'm solving for t, which means I need to get rid of these numbers, and I'll get rid of the coefficient once again as my first step. So let's divide by this. Oops. Let's divide by the correct number here. 5.451. Whoosh. And I don't know what that number is, so I'm going to plug that into the calculator. Let's clear some of this out. I've got 7 divided by 5.431, excuse me, 451. Yikes, I'm not able to read this number correctly. And, you know, this time it's kind of an ugly number. So I'm going to use this. I don't want to round in the middle of my work, so I'm going to keep this running in my calculator. I'm going to put 1.284 just so I have something here. 1.284, but I'm going to put my little dot, dot, dot. That's just to remind me that I'm using the exact number in my calculator. E to the 0.01165 t. And now I'll do the natural logs again. So I've got the natural log of this equals the natural log of this. That basically goes away. And I'll have the natural log of this number that's still running in my calculator. You can store it in your calculator if you would prefer. Equals this. And now I just have to divide by this constant that the United Nations had figured out. 0.01165. And I'll have t is approximately, let's see, I need to do this natural log. And I'm going to do the natural log of that previous answer. So I'm pressing second answer. So I'm using the exact number that I had just calculated. Or you can store this in and store it in as whatever letter and plug that letter in. And now I'm dividing by that constant 0.01165. Believe that's correct. And let's see what we have. 21.469, let's say. 21.469. So t is 21.469. Now we need to answer this question. We solved what t is, but let's understand what that means. If t equals 0 represents 1990, then t equals 21 represents 21 years after 1990. So if I'm going to add 21 years to that, I believe we're talking about 2011. If you want to get a whole lot closer, you can talk about what fraction of a year is 0.469. That's probably sometime in June or something. But I'm just going to say the year 2011 must have been when we reached 7 billion people. I believe that's pretty close, but again, this was a model back in 2002, and there you go. Okay, so let's look at our final example. Example 6. There is a college whose campus size is 5,000 students, and it says one student has the flu. Oh no. It says the spread of this flu is modeled by this equation. This is a logistics growth model where t is measured in days. So our first question, kind of a simple question, it says how many are infected after 5 days? Well, t is right here in this little exponent that happens to be down in the denominator. That just means plug in 5 for t. Since t is measured in days, we'll just plug the 5 in right there, and that's what y will become. So we've got 5,000 divided by 1 plus 4,999 e to the negative 0.8 times 5. So we can just plug that in. I want to make sure that you understand that these are not like terms. I cannot take the 1 and add it to this coefficient. This is a coefficient that's multiplied to something else, and this is just a 1. We cannot add those two things together. All we have to do is plug this into the calculator, and we'll see how many people are infected after 5 days. So you can try, whoa, you can try and plug all of this into your calculator all at once if you really want to. I might just do it in pieces and figure out what negative 0.8 times 5 is. I'll just get that coefficient, excuse me, that exponent, negative 0.8 times 5. So that's the exponent that I'm talking about. And then I need to do e to that number. So I'll do e, second e raised to that number. So I'll do caret and then that answer, enter. And then I need to multiply that by 4,999. So I'll multiply by 4,999, enter. And then I'm going to add 1, enter. And then I have to take 5,000 divided by that number. So I'll take 5,000 and I'll divide by that previous answer. So I'm okay doing it that way. If you'd rather do it all at once, hopefully you don't mess up in your parentheses and you get the same number, which is 54.019. So 54.019, and we're talking about people. Maybe I should say students. So it's about 54 students and I guess the beginning of another student, somebody's left toe. So the second part of our problem is a little bit trickier. It says if the college policy is to cancel classes when 40% of the student body is sick, when will this happen? Well, hopefully this college has learned that there are actually medications and things like, you know, coughing into your sleeve or your hands or something like that so that you're not just coughing all over everybody, such that 40% of the student body is sick. But okay, let's see what happens. First of all, we should probably figure out what 40% of 5,000 students is. So 40% of 5,000 students, multiply that together, and I can do that quickly in my head, that's 2,000 students. So we're talking about when will 2,000 students be sick? And that is representing this y value. Maybe not this y value, but rather this y value. Obviously, t is going to be the thing that we're looking for. So we want to know, when is 2,000 going to be equal to this model? 5,000 divided by 1 plus 4,999 e to the negative 0.8 times t. That's my equation that I need to solve. And t will then represent how long it takes before 40% of the student body is sick. So the first thing I do, actually, since this t is in the denominator and I don't like when my variable's in the denominator, I'm actually just going to take the reciprocal of this side of the equation as long as I do the same thing to this side of the equation. That's just one little quick thing that I'm going to do. I'm going to do 1 divided by 2,000 equals the 1 plus 4,999 e to the negative 0.8 t divided by 5,000. I'm just going to take the reciprocal of both sides, and therefore my variable is up in the numerator. I like that. I'm going to get rid of this 5,000. Since it's in the denominator, I'm going to multiply it away. So I'm multiplying by 5,000. 5,000 divided by 2,000, I can cancel out all of the zeros, and I get 5 halves, which I might just change to 2.5 just to make it easier to plug in. And I just have my numerator now. Still solving for t. The next number to go, get rid of this 1. I'll subtract 1 from both sides, and I'll have 1.5 is equal to this 4,999 e to the negative 0.8 t. One more thing to go before I get my e. Let's get the 4,999 out of there. We'll divide that. I got to come over here. I'm going to have e to the negative 0.8 t is equal to, let's do this on the calculator so we can have something there. We've got 1.5 divided by 4,999. It's probably not going to be the best decimal. No, it's not. It's about 3.00, I'll say 3.001. Actually, this is a decimal. Yeah, so I don't really like that. I mean, I'll go ahead and write it as it's actually 0.0003 dot, 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 because that c that e to the -4 means times 10 to the -4, so the decimal point is actually all the way over here. It doesn't matter because I'm just going to store this in the calculator or just use this number when I need it in my calculator. The last thing I need to do, actually two more things, I need to do the natural log of both sides. I might just squeeze it in right in here so that I can cancel this away. Make sure you do it to both sides, and I'll have -0.8t is equal to, let's do the, I'll just keep that as natural log of 0.0003 dot, 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 dot. This is an exact number that I'll eventually use, and then divide by -0.8, and I'll have my answer for t. A little bit trickier here. And let's see what we've got. So we've got the natural log of that previous answer, this long decimal here that I've got, and then divide that by -0.8, and I'll have my answer of 10.139. 10.139. Now this is a little scary if you think about it, because if you remember what t is measured in days. So this is not even 2 weeks before 40% of the student body is sick. So again, hopefully people with the flu do not go out in public and get other people infected. Hopefully they just stay home, get some medicine, and take care of themselves. Thanks for watching this tutorial, and we'll practice more application problems in class next class. Bye-bye.